Okay, I'm just going to take a minute to explain what specific latent heat of vaporization is, and then hopefully we can do a quick calculation for the specific latent heat of vaporization of water. So, what is specific latent heat of vaporization? Well, it's all to do with vaporization, which is turning something from a liquid to a gas. And the specific part, you might recall from specific heat capacity, has to do with per kilogram or per unit mass. So it's something about vaporizing, turning from a liquid to a gas, a certain amount, a certain mass of substance, usually a kilogram. And what is it? Well, it's the energy required to do that. So the specific latent heat of vaporization is the energy required to vaporize 1 kilogram of a substance. That is to turn it from a liquid to a gas. So if you want to turn a kilogram of water from liquid water to gas water, water vapor, you have to supply energy to do that. It's not going to do it by itself. You have to heat it, supply heat energy, and that is going to vaporize the liquid water into water vapor. Small technicality that it's the energy to vaporize it without changing the temperature. We'll talk about that in a minute in the case of the water I've got over here. So, let's have a look at this water I've got in here in the kettle. We're going to see if we can estimate the latent heat of vaporization of it. So, I've got a kettle full of water, and it's just coming up to the boil now. I've got it on a balance, so you can see the combined mass of the kettle and the water all together. And if you look at it, hopefully you can see that the reading on the balance is going down. The water has now reached its boiling point, around 100 degrees. Water is being vaporized from a liquid to a gas, and as the gas escapes, the reading on the balance is going down. Now, that thing I was saying about a constant temperature before, without changing temperature, the water's now at its boiling point, and once the water reaches its boiling point, its temperature does not change. It remains at 100 degrees. So what I'm going to do is record the mass reading, and then a minute later or so record the mass again and see how much water we vaporized. I'm then going to do some calculations as to how much energy went in, and we can estimate the latent heat of vaporization. So I'm going to start now. That was on 1509 grams. And then we'll leave it to run for a minute, and I will write down the reading when a minute has elapsed. Then we'll do the calculations. Now, the way I'm going to calculate the energy input is because I know the power rating of this kettle. It says underneath the bottom of it that it's a 2000 watt kettle. That means 2000 joules per second of energy are being transferred to the water. So if I know how long I've been transferring energy for, 60 seconds, I should be able to work out the power in. And in fact, I've already done that calculation since I knew that in advance. So all I've got to do really is work out, by reading off the balance, the mass of water that has vaporized. And here we go, the time's coming up. And I'm going to say it is 1458 grams. Right, I can turn it off now. So, let's just have a quick look at the calculations and see what they say. Now, energy in equals power times time, which was 2000 watts times 60 seconds, which is, if I take the 2 times the 60, that's 120, and then there's the whole 1000 there, so 120,000 joules. Okay, and the mass vaporized is 1509 grams, which I'll call 1.509 kilograms, minus 1.4 8 kilograms, which is, how is my mental maths? It looks like, if I were to do it in grams, 51 grams, which is 0.051 kilograms to me. So what we've worked out is the energy required to vaporize, well, not a kilogram, 0.051 kilograms, which is not a kilogram. However, we should be able to, nonetheless, work out the latent heat of vaporization. So, the formula for it is over here. E, the energy required to vaporize, equals m, the mass in kilograms, times the latent heat of vaporization. Now you've got to be very careful with units here because the units could be different. If you put in your energy in joules and your mass in kilograms, your latent heat of vaporization is going to be in joules per kilogram. But if you put in the energy in kilojoules, then your latent heat of vaporization is going to be in kilojoules per kilogram. And likewise, if you're doing it the other way around, if your LV goes in kilojoules per kilogram, your energy is going to come out in kilojoules, and so on. So, what we're going to do is rearrange this equation here for mass. Now that would be mass equals E over LV. And if we do that over here, we're going to have 120. Now look, I'm going to turn this into kilojoules already because we're going to lose track. 120 kilojoules divided by 0.051 kilograms to get the latent heat of vaporization of water. Now I'm going to chuck that in a calculator because I don't fancy doing that. It's close to being something that's easy to do, but it's not quite. 120 kilojoules divided by 0.051 equals, we'll call it 2400 kilojoules per kilogram, rounded to two significant figures. And that's not actually horrendous for a quick little practical that we did, without much effort. The true answer is apparently 260, which you'll notice is a little bit less. And just like with our specific heat capacity practical, the reason we've overestimated the energy is because some of the energy was being lost to the surroundings. So not all of the energy there was being used to vaporize the water. Some of the energy was being lost to the surroundings, resulting in a slight overestimate. But it's not terrible by any stretch. Actually, since the true value I've quoted there is to 3 sig fig, let me quote this to 3 sig fig as well, which from the calculator is 2350. So it's not horrendous by any stretch. So just to reiterate then, the specific latent heat of vaporization is the energy required to vaporize 1 kilogram of the substance without changing its temperature. So if you want to vaporize something, you've got to put energy in. This formula tells you how much energy you have to put in to vaporize a certain mass of substance. Now, just to say that it works the other way too. So if you put this energy in to vaporize stuff, you get that energy out if you condense it back. So when water goes from a gas to a liquid, this energy is released. And it's not often everyday situations where this happens. There's quite a lot of everyday situations when you vaporize stuff. There's not a lot of everyday situations where you condense stuff and then notice this extra energy coming out. But it does happen in a couple of situations. I haven't got a border up. Right. So there's 2 situations that spring to mind where energy is transferred by something condensing. And it's both water. One of them is just a steam burn. Now, over here, I've got the old kettle that I had before. Okay, now if I get this boiling, you'll notice that loads of steam starts coming out of here. Okay, now I don't know if you've ever burnt yourself with steam, but if you have, you'll find it's a very painful thing to do. Okay, now that's not because the steam is conducting lots of heat. to your hand, okay? If you touch a hot metal pan, you get burnt because the metal's an excellent conductor and it conducts heat to your hand rapidly. But as you know, gases are poor conductors of heat. So this steam here, I don't want to put my hand in it for long, okay? The water vapour coming out of there is not a brilliant conductor of heat because it's a gas. However, if the steam condenses onto your fingers and onto your hand, it releases the energy that was tied up in it from when it was vaporized. And that energy is released in the form of heat, and it heats up your hand. So if you put your hand, I'm not going to do, even that hurt quite a lot, okay? If you put your hand in a load of steam, you get quite a bad burn, not because it's conducting lots of heat, but because it's condensing and delivering that energy back to your hand. The other common situation is if you like posh coffee, okay, you might go to a coffee shop where they make you a nice coffee with some hot milk, and the hot milk, they pour it in there with a nice pattern and stuff like that. How do they heat the milk up? You might have seen it. Basically, inside the coffee machine, there's a pot of water with a heater inside it, and the heater, and it's all closed up, the heater heats the water up until it vaporizes. So it's supplying this energy to vaporize the water. The water vapour then goes through a pipe into a jug full of milk. Okay. Now you notice when they do this that steam doesn't come out the top of the milk. No steam comes out of there. Where's the steam gone? Okay, you had steam going through this pipe. Where's it gone? Well, it's all condensed in the milk. Okay, so the water vapour has condensed inside the milk. So when the water vapour condenses, it gives back that energy that was put into it here to vaporise it. So to turn it from liquid to gas took energy. Then when it turns from gas to liquid, it releases that energy again, which heats up your milk. So the milk doesn't get hot because hot steam is passing through it. It's not like hot steam is passing through the milk and then on the way out, as it goes through, it's transferring the heat. No, it's the steam itself condensing inside the milk, transferring the energy that was put into it here. So this is basically a method for transferring heat from the heater to the milk, but via steam. Steam is the intermediary. And one of the other advantages is because the steam is churning up the milk, it can suck air into it and put little bubbles in it and make it all nicely textured. So those are two typical situations where the reverse process happens, where a gas goes to a liquid and energy is released, but it's not common. And that's where the word latent comes from, by the way, just in case you're wondering what these pointless words are for. Latent means kind of hidden or locked up inside it or something. So the idea is that if you vaporise something, there's energy hidden within it. In any gas, there's energy just waiting to be released if you can condense it. So if you condense the gas into a liquid, you get this hidden heat energy out. So I hope that's been at least a little introduction. Really, you're not going to get a true understanding of this until you start answering some questions and doing some practical work, but hopefully it's enough just to give you a bit of an idea about what's going on.